This is the 18th lecture, and the topic is Fourier analysis of discrete time signals and systems, and today is the beginning of this topic. You recall one of the differences between continuous time functions and discrete time functions, that e to the j omega 0 t in the continuous time case is always periodic, right? It is periodic. On the other hand, e to the j omega naught n is not necessarily periodic. It is periodic only if omega 0, well, 2 pi by omega 0 is rational. That is, it is of the form, let's say, capital M by capital N. Otherwise, it is not periodic. So there is a difference between continuous time systems and discrete time systems. The difference also arises in the case of signals, and some of the differences are very distinguishing features for discrete time signals, and one must note that. And this is one reason why we shall discuss this topic in a slightly different manner as compared to continuous time signals. In the case of continuous time signals, we started with periodic functions, and we first did Fourier series, and then Fourier series when the spectrum, the interval between two lines in the spectrum approached 0, we got what is known as the Fourier transform. From Fourier series we went into Fourier transform, and we are pretty logical and fussy about the various steps. We considered existence, we considered uniqueness, we considered whether the transformation is one-to-one and things like that. In view of the experience that we have gained in the case of continuous time signals, we shall now proceed a little more heuristically rather than very rigorously. All right. For example, we shall play the tune of Fourier series for the discrete time signals at a low key, and we shall come back to this discrete time signal Fourier series a little later in the discussion. We will start with Fourier transform for discrete time signals. The definition, if you recall the definition of Fourier transform in the case of a continuous time signal, x of omega is given by minus infinity to plus infinity x of t e to the minus j omega t dt. This is the definition of Fourier transform in the case of a continuous time signal. Now, if you want to go from this to the discrete time case dt signal, the discrete time signal exists only at t equal to nt. It does not exist anywhere else, and therefore the discrete time signal is not a continuum, and it does not make sense to integrate a discrete time signal. The integration now becomes a summation, that is, you take the two ends and compress it. So in the case of the discrete time signal, it would be a summation, and x of t is now x of nt. The interval, the smallest interval of time, is now capital T, all right, capital T, and this becomes e to the minus j, well, what do I put for omega? Pardon me? 2 pi by, if capital N is a period, well, let's put omega for the time being, all right, and small t is capital NT, all right. This would be the form of the Fourier transform. As I said, I am going a little heuristically rather than very rigorously. This would be the form of the Fourier transform, in which if I write, now this step is important, if I write omega times capital T as equal to capital omega, all right, then my definition shall become e to the minus j n capital omega, and then I argue that capital T after all is a multiplying constant, and in a summation it can come out, it's not essential as in the case of the integral, and therefore capital T we can ignore. Another way of saying this, we normalize capital T to unity. Alright, so capital T we ignore, and you know that discrete time signal, the time interval capital T is not explicitly written. We write this as x of n, and therefore finally we get the definition of Fourier transform of a discrete time signal x of n as equal to, if we call this capital X, and you recall what capital omega was. Let's recall capital omega was put as small omega times capital T, which means that if it is an analog signal, a continuous time signal which has been sampled at intervals of capital T, then small omega is the actual frequency in radians per second, that is twice pi times a number in hertz, that multiplied by the sampling interval capital T. This is the interpretation of the angular frequency for the digital case, which we shall call the digital frequency. You must distinguish between small omega and capital omega in the case of a discrete time signal which has been derived from a continuous time signal. Otherwise there is no problem. There is no problem. Alright, if you have a continuous time signal which has been sampled to give you a discrete time signal, then this frequency capital omega is related to the actual frequency in radians per second by omega times capital T. So this is a normalized frequency, and as you shall see in a moment, capital omega, the range is 0 to 2 pi, or the range of omega, range of capital omega is simply 2 pi. You can start from minus pi, you can go up to plus pi, because the phenomenon is repetitive, which is a distinct difference between discrete time signal and a continuous time signal. But let's go ahead with the definition. Capital X of omega is defined as, I have shown you the derivation how from the continuous time case we go to the discrete time case. You can now take this as a matter of definition, that is where n goes from minus infinity to plus infinity. This is the definition of Fourier transform of a discrete time signal, and you can easily see now that if we change omega to omega plus 2 pi, alright, capital X of omega plus, let's say, r times 2 pi, where r is an integer, 0, positive or negative, it doesn't matter, and you can easily see that if I substitute omega plus r 2 pi in this exponential, the function does not change, and therefore this is equal to capital X omega, and therefore the spectrum, if we call capital X of omega is the spectrum of x of n, the spectrum of a discrete time signal is periodic, and the period is, how much is the period? With a period of 2 pi. This is a distinct difference between discrete time signal and continuous time signal. In the case of continuous time signal, capital X of small omega, that is the spectrum, may or may not be periodic. Hardly ever, in none of the examples that we worked out, we got a periodic function. But here it is periodic to start with. The definition itself makes sure that it is periodic. Alright. Is this a one-to-one transformation? That is, alright, we are given an x of n whose Fourier transform is capital X of omega, which is equal to summation xn e to the minus jn omega, n equals minus infinity to plus infinity. Well, we can go from x of n to capital X of omega. This arrow, is this arrow true? That is, can you go from capital X of omega to x of n? If this is to be a linear transformation, then it must be true. It must be a one-to-one transformation, and if this is true, then we can easily show that the reverse, that is, we can reconstruct or get x of n given capital X of omega by the following method. That is, what you do is we multiply capital X of omega by e to the j, let's say r omega. we multiply this and then and then we integrate this. Now since x of omega is periodic, integration has to be over one period. It does not make sense to integrate from minus infinity to plus infinity. Integral over one period and then we divide by 2 pi. We divide by 2 pi. Well, if I do that, then you see in the right hand side, if I multiply by e to the j r omega, then in the right hand side it would be e to the j r minus n omega. Alright? And the integral of this, if you multiply by x of n, the integral of this over one period is 0 unless r is equal to n. And if r is equal to n, then the only term that remains is x of n. The integral d omega gives you 2 pi and 2 pi cancel. I am omitting these steps. These are routine. We have done it once or twice. And therefore, it simply becomes equal to x of n. No, I have made a mistake. X of r, that is correct. It becomes x of r. Is there a question on this? Do we have to go through these steps? Or you can do this yourself. Alright. And therefore, our Fourier transform pair is x of n to x of omega, which is, I am writing this again and again so that it gets imprinted in your mind, x of n e to the minus j n omega, and capital x of omega. From this you can go to x of n, where you have to carry out an integration. But the difference is that the integration, unlike the continuous time case, it is an integration over a period. You can go from 0 to 2 pi or minus pi to pi, it doesn't matter. But the interval has to be a period. X of omega you multiply by e to the j n omega d omega. This is very similar to the inversion formula for continuous time signals, but the difference is that the integration is over 2 pi, only one period. Let me emphasize the distinction, the differences between CTS and DTS. Fourier transform for a continuous time signal is not necessarily periodic. Fourier transform for a discrete time signal is mandatorily periodic. If it exists, then it must be periodic. Well, I am coming to existence conditions a little later. And the inverse transform is given by an integration in both cases, but the integral in the continuous time case has to go from minus infinity to plus infinity, that is for all frequencies, whereas this integration is only over one period. So in a sense, the Fourier transform for discrete time signals is a simpler concept as compared to the continuous time signal. At least in one of the integrals, you have reduced the range of integration. Instead of minus infinity to plus infinity, you had minus pi to plus pi, or 0 to pi, 0 to 2 pi, and so on. Then the question of existence. Well, in an exactly similar manner, one can show that the Fourier transform for the discrete time signals exists either for absolute integrability of the sequence, that is x of n. Well, no question of integration now, it has to be summation. Either x of n is absolutely summable for all values of n, that is, this should be less than infinity, or it should have finite energy, that is, x of n mod squared n equal to minus infinity to plus infinity should be less than infinity. Alright. One of these conditions, if it is satisfied, then the Fourier transform shall exist. I repeat that these are sufficiency conditions. They are not necessary. Signals which do not obey either of these conditions can also be transformed, can also be Fourier transformed. You recall that in the continuous time case, besides, well, one of the conditions was the energy condition, that is integral minus infinity to plus infinity mod xt squared dt has to be less than infinity. And the alternative was, where the absolute integrability was brought into the picture, there were conditions on maxima, minima and discontinuities You see, in the discrete time signal, these are not relevant, they are not meaningful. What do you mean by discontinuity in a discrete time signal? Discrete time signal itself is a discontinuous signal. There is no question of maxima or minima, because it is not a continuous function of time, and therefore these conditions are therefore much simpler conditions as compared to the continuous time signal. Is the point clear? Let's get a feel of this by taking some examples. The first example that we take is x of n is a to the n un, where a, let's say, lies between 0 and 1. A is a positive quantity lying between 0 and 1. You can extend it to a negative a also. Now, if I apply the definition, capital X of omega is given by x of n, that is a to the n un e to the minus j n omega. N goes from minus infinity to plus infinity, and because I have a u of n, my lower limit can be substituted by 0, and therefore this becomes equal to infinity n equals 0 a e to the minus j omega whole to the n, and this is a geometric series. It is summable provided the mod of this function a e to the minus j omega is less than 1, and this is already guaranteed. A lies between 0 and 1, and the mod of e to the minus j omega is equal to unity, and therefore this is simply given by 1 minus a e to the minus j omega. That is the Fourier transform of the signal a to the n un, and you see a to the n un is like an exponential signal. It decays with time. The envelope goes like this. This is the signal. A is less than 1, therefore it continuously decays. It's like an exponential signal. A to the n un plays the same part as that of exponential signal in the continuous time case. Let's write this down. A to the n un is the Fourier transform of 1 by 1 minus a e to the minus j omega. Exactly like the continuous time Fourier transform, we can find its magnitude and phase spectrum. The spectrum is a continuous function of omega, and if I take x of omega, the magnitude and phase can be written down like this: 1 minus a cosine omega, then plus or minus plus j a sine omega, and therefore mod x of omega is equal to 1 by square root of, you can check, 1 plus s squared minus twice a cosine omega. Is that okay? Cosine or sine? Cosine. And the angle of x of omega is given by minus tan inverse of a sine omega divided by 1 minus a cosine omega. And if I plot now mod of x omega versus capital omega, we get the magnitude spectrum. If I plot angle versus omega, then we get the phase spectrum. Let us see what the spectra look like. Let me repeat: mod x of omega is equal to 1 by square root of 1 plus s squared minus twice a cosine omega. If I plot this function versus omega, all right, you see that at omega equal to 0, the function should be a maximum, isn't it right? The dependence on omega is only through this term, so the function should be maximum, and the value should be 1 by 1 minus a. All right, let's say this is 1 by 1 minus a, and that when this changes to a plus sign, plus 2a, which happens at omega equal to pi, and therefore at omega equal to pi, the function has a minimum value, and the minimum value is 1 by 1 plus a. All right, and therefore the variation of the function, the spectrum, shall be like this. If this is minus pi then the variation would be like this. And then what will happen? It shall repeat, it shall make a periodic excursion like this. So this is the magnitude spectrum, and it is very clear that it is periodic if you go on plotting this. And if you plot the phase, well, what observations can we make about phase? Phase is also periodic, it has to be, it is also periodic, but you know the phase is an odd function. And what is the phase at omega equal to 0? It is 0. At omega equal to pi, it is also 0. And therefore, the phase varies like this. Oh, there is another interesting point. If omega equal to 0 minus, will the phase be positive or negative? Positive. Alright. If omega is 0 plus, the phase shall be negative. Alright. So we can now plot the phase. The phase function will look like this. If this is pi, is minus pi, well, the phase function looks like this. At pi, it again goes to 0. It's positive, so it's like this. At omega equal to 0, it is 0. Pi, it is 0. Minus pi, it is 0. And in between there must be a maximum. In between there must be a minimum. It's an odd function, and it continues. It is periodic also. All right. The next, a little more complicated function is an exponential function which decreases exponentially on both sides. That is, it is not a multiplication by u of n, but it decreases on both sides. So we have a sample here, we have a sample here, we have a sample here, and so on. This function obviously is of the form e to the minus mod n for all n. It exists for all n, minus infinity to plus infinity. So this is x of n. And if we want to find out capital X of omega, it is summation. Now I break up the summation into two parts. That is, I go from n equal to minus infinity to minus 1. That is for all negative n. Then the function should be e to the minus n or plus n? E to the plus n. All right. Then e to the j n omega. And similarly here it should be e to the minus n, where it goes from n equal to 0 to infinity, and then e to the j n omega. Where I made a mistake. Can we? E to the minus j n omega in both cases. That does not change sign. All right. So if we find these summations, and then simplify, I'll leave the simplification to you. Well, the trick essentially is that I put n equal to minus m here. Then I get m equal to infinity, plus infinity, and m equal to 1. N equal to minus m, so this becomes minus m, and this becomes e to the j m omega. All right, and then I sum this up. Is that okay? So the first sum shall be, this sum shall be 1 minus a e to the power, this sum shall be 1 minus a e to the power j omega.
Where did you get that is? There's no a sign though.
I beg your pardon, this is a. That's what I was missing. It's not exponential. Well, it is exponential, but a can be put as e to the power b. This is a to the power minus n. In the previous case we had taken a to the n un. So here we take a to the mod n. Do you understand why this is plus e to the j omega? Yes? Because it is e to the j m omega, m going from plus 1 to infinity. But then I have made a mistake. It should be, I must take 1 out. Isn't that right? This summation does not include m equal to 0. I have included m equal to 0 here, so I must take the constant term out. plus 1 by 1 minus a e to the j omega. Now if you simplify this, then the function that you get is my x of n is e to the a to the minus mod n capital X of omega. If you simplify this, you get 1 minus s squared divided by 1 minus twice a cosine omega plus s squared. Tell me, is this this is a real function of capital omega. What about its phase? Can it change its phase?
Zero. Phase is 0.
Phase is 0 always? Can it not be negative? Capital X of omega, can it be negative? Well, 1 minus s squared, if a lies between 0 and 1, then 1 minus s squared is always less than 1. It cannot change sign. Alright. What about the denominator? All that can happen, the maximum and minimum values of this are 1 plus a whole squared and 1 minus a whole squared. And if you see at the minimum, 1 minus a squared divided by 1 plus a whole squared, this becomes 1 minus a by 1 plus a, and the maximum would be 1 plus a divided by 1 minus a, and therefore it cannot change its sign, right? So the phase spectrum is identically 0 at all frequencies. It's only the magnitude spectrum that we have to draw. And the magnitude spectrum, as you see, at omega equal to 0, is this a maximum or minimum? Is this a maximum or minimum? Maximum, because the value is 1 plus a divided by 1 minus a. And therefore, the general nature of the plot would be like this. There is a maximum, and then there is a minimum, maximum, minimum, and so on. Not quite sinusoidal. And the values, the minimum occurs at, can you tell me where the minimum occurs from the expression?
Pi.
Omega equal to pi. So plus pi and minus pi, cap omega, and then this is capital X of omega. And this value is 1 plus a divided by 1 minus a, and this minimum value is 1 minus a divided by 1 plus a. This is the nature of the spectrum, and as you can see, the spectrum is indeed periodic. Our next example is that of a rectangular function, a rectangular pulse. In the continuous time domain, we had lot of fun with this function. In the discrete time domain, what we have is, we have samples like this. Well, I have shown a few samples, we can have more. And let's say this is the 0th sample, this is 0, this is plus n1, this is minus n1. This is x of n versus small n. The question we ask is, what is capital X of omega? Well, obviously, capital X of omega by definition is equal to summation x of n, which is, for simplicity, let's say the value is 1, and the summation will be taken not from minus infinity to plus infinity, but minus n1 to plus n1. So n equal to minus n1 to n equal to plus n1, and then we have 1 e to the power minus j n omega. That's it. Now to sum up this is a finite summation. It's very easy to do. To sum up this, let's say e to the minus j omega is equal to w. I'm introducing this symbol w. W shall be used later in the case of the FFT or DFT. Alright. Then I have this summation becomes w to the minus n1 plus w to the minus n1 plus 1 and so on, up to w to the minus 1 plus w to the 0 plus w to the 1 and so on, up to w to the plus n1. And if from this I take w to the minus n1 out, then I get x of omega as w to the minus n1. What do I get in the bracket? 1 plus w squared and so on up to w to the 2n, and therefore this is equal to w to the minus n1. What do I get? 1 minus w to the 2n plus 1 divided by 1 minus w. Now let's look at it like this, w to the minus n1. Let's take w to the n1 plus half out. Then I get w to the n1 minus n1 plus half minus w to the n1 plus half. In the denominator, let's take w to the half. Then I get w to the half minus w to the, no, first we have minus half and the next is plus half. Now you notice that these terms cancel with each other. W to the half cancels with w to the half and w to the n1 cancels with w to the n1, and therefore this shall be, now you recall that w is equal to e to the minus j omega, and so if you substitute this, then you simply get the sinc function expression, that is sin x by x form, and what you get is sine of omega n1 plus half divided by sine of, yes, omega by 2. It is of the same form, sine nx over sine x, but there is a distinct difference. This spectrum x of omega is no longer a damped sinusoidal wave. It periodically repeats itself, and if we plot over the basic period, that is minus pi to plus pi, the plot looks like this. My function is capital X of omega is equal to sine of omega n1 plus half divided by sine of omega by 2, and if I plot this, let's take a specific value, let's say n1 equal to 2. Can you tell me what the value at omega equal to 0 shall be? Pardon me?
5.
5, that is correct. So it shall be 5. Then in between it shall show a minimum, and at pi it will go like this. Then what happens? Then it repeats periodically. That is, it goes like this and shows another peak at, what would be this value? 2 pi. And this repeats on the left hand side also. This repeats. It's no longer a sin x by x form for all values of x. Alright? This is the basic period, minus pi to plus pi, and then it's a periodic repetition. And therefore the spectrum, well, one of the consequences of this, that there is no dampening of the spectrum which happens in the continuous time case. One of the consequences of this is that there is no Gibbs phenomenon. You remember Gibbs phenomenon? If you want to approximate Gibbs phenomenon, if you want to approximate a discontinuous function by a continuous function, then Gibbs phenomenon occurs at the points of discontinuity, just before and just after. There are overshoots and undershoots. Well, this does not occur here. It can be more interestingly brought out by considering the singularity function delta n. We can't call it a singularity function because delta n itself is a discontinuous function. It is simply 1 at n equal to 0, and it is 0 at all other values. Now can you tell me what is capital X of omega? If I take the summation and apply the summation, it's simply 1, which means that if I plot X of omega versus omega, well, it's simply a flat spectrum like this. It's simply a flat spectrum. Alright. Now suppose we want to approximate this flat spectrum by a band limited spectrum. That is, suppose we want to approximate, now follow this point carefully. This is very interestingly brought out and very demonstratively. Suppose, well, we can't have a flat spectrum from minus infinity to plus infinity. It's a very costly spectrum. Spectrum is a very costly phenomenon. So what we do is we say, all right, we have a spectrum which is flat from, let's say, minus w to plus w. Then this, we shall call this as x1 of omega. Obviously, x1 of omega will tend to capital X of omega as w tends to infinity, and we should expect something like a Gibbs phenomenon. This is what we did in the continuous time case. Well, fortunately, that is not the case. If you have a capital x1 of omega, which is like this, minus w to plus w in capital omega, then x1 of n, if you take the inverse Fourier of this, that is 1 by 2 pi minus w to plus w, all right. So over one period, we assume that w is less than pi, agreed? Then it's minus w to plus w, or if it is greater than pi, then you take from minus pi to plus pi, minus w to plus w, and then you have what? If you call this as 1, e to the j n omega d omega. And you can easily see that this is given by sine of n w divided by pi n. If you integrate this, then this would be the result. Now, suppose, well, what's the value of this function when w equal to pi? When w equal to pi, what happens? W equal to pi means capital X1 of omega is a periodic function, and therefore it repeats, and therefore it becomes flat. Capital W does not have to go to infinity to make my flat spectrum. Let's come back here. Capital W only has to go to pi, that's all, because this spectrum has to be periodic, all right. So what happens is, when w equal to pi, I should get the flat spectrum. What is x1 of n under this condition? When w equal to pi, you see that sine of n pi is unconditionally 0, except at n equal to 0, where the denominator also is 0. So it becomes a 0 by 0 form, and you can see that it is indeed a discontinuous function. It gives delta n, that is, the value becomes 1, all right. When w becomes pi, sine of n pi by n pi becomes simply equal to 1. In other words, when w equal to pi, x1 of n is delta n. There is no Gibbs phenomenon, there is no overshoot, there is no undershoot. This is one of the simplifications that you get in the discrete time signals. Now let's enter into a little more complicated expressions. X of n, next example, is an exponential, truly exponential signal, e to the j omega naught n. You know that this is not necessarily periodic in n. It is periodic in n if 2 pi by omega 0 is a rational number. But it is periodic in omega 0, isn't that right? It is periodic in omega 0 because if you put omega 0 to omega 0 plus r times 2 pi e to the power j, this multiplied by n is indeed equal to e to the j omega 0 n. So it is periodic in omega 0. This signal e to the j omega 0 n is periodic in omega 0, and we shall show that is Fourier transform. Well, what was the Fourier transform of e to the j omega naught t? If it was the continuous time case, what was the Fourier transform? It was twice pi delta of omega minus omega naught. You will see now that it is not just one impulse, it is not just one delta function, it is a periodic repetition of the delta function. Now does that surprise you? It should not, because any spectrum of a discrete time signal is periodic, and therefore it has to be periodic. In fact, we will show that capital X of omega is equal to summation 2 pi delta omega minus omega 0 minus 2 pi L. This is the repetition, where L goes from minus infinity to plus infinity. This stands to logic. From common sense, we know that capital X of omega has to be periodic, so it has to be sum of delta functions. Now, precisely this form can be argued out by going the reverse way. That is, given capital X of omega is equal to summation infinity L equal to minus infinity 2 pi delta omega minus omega naught minus 2 pi L, what is the corresponding X of N? Let us find that out. If I take the definition 1 by 2 pi integral over 2 pi, alright, X of omega, that is summation infinity L equal to minus infinity 2 pi delta omega minus omega naught minus 2 pi L, then it has to be multiplied by e to the power j, yes, n omega, then d omega. Now, let us see. If we look at this function, a plot of this function, we have something like this. If we plot X of omega and consider L equal to 0, so I have a delta function. It is not an impulse, it is a delta in the discrete domain, so it is a finite length. We have a delta function, well, its amplitude would be 2 pi, but let us ignore the amplitude. We have a delta function with L equal to 0 at omega equal to 0. With L equal to 1, we shall have at, well, this is omega 0, this is omega 0 plus 2 pi. Then we shall have 1 at here, omega 0 minus 2 pi, alright, and so on. Then we shall have 1 at omega 0 plus 4 pi. We shall have 1 at omega 0 minus 4 pi. The purpose of my drawing this figure is the following, that within one period of this function, this is a periodic function, within one period, let us say minus pi to plus pi, there occurs only one delta function. Isn't that correct? There occurs only one delta function, and therefore this summation will, if I integrate over one period, in this summation only one delta function shall be involved. And if this delta function is, let us say, this particular term omega minus omega 0 minus 2 pi L, then the value is 1. Please follow this carefully. 2 pi and 2 pi shall cancel, you can ignore that, alright. In this integral over one period, only one delta function shall be involved, and let this delta function occur at omega 0 plus 2 pi L, alright. If I substitute this here, instead of omega, if I substitute omega 0 plus 2 pi L, what is it that I get? I simply get e to the j n omega 0, and that is the proof. That is e to the j n omega 0, this signal has this Fourier transform, alright. I repeat, in the continuous time case, e to the j omega 0 t gave only one impulse at omega equal to omega 0. In the discrete time case, it gives a series of impulses. These impulses are of course not impulses in the continuous time sense, their length is finite, they only occur at a particular value of omega, alright. Now it's a very easy matter now to argue what would be the spectrum of, let us say, x of n, which is cosine of omega 0 n. Need I remind you that e to the j n omega 0 was not necessarily a periodic function in n, but it is necessarily a periodic function in omega 0, and therefore the spectrum that I drew, that is a continuation, a repetition of deltas, that has nothing to do with periodicity in the time domain, it is only in the frequency domain. Alright. Similarly, cosine of n omega 0 is not necessarily periodic. It will be periodic only when 2 pi by omega 0 is a rational number. Alright. Now 2 pi cosine of omega 0 n can be written as half of e to the j n omega 0 plus e to the minus j n omega 0. And you can treat this signal x of n as a linear combination of e to the j n omega 0 and e to the minus j n omega 0. And therefore, you can find out the spectrum of this, that is capital X of omega by capital omega, by superimposing the spectra of these two signals. Alright, and what you will get is something like this. If this is omega equal to 0, you remember we had one at capital omega 0 due to this term e to the j n omega 0. So we shall have another at minus omega 0, and then where would the next one occur? Minus omega naught minus 2 pi. Alright, and similarly here plus omega naught plus 2 pi, and so on. This spectrum shall now be an even spectrum, isn't that right? It's an even spectrum, that is, it is symmetrical around capital omega equal to 0. Is this point clear? Alright. Now in the rest of the few minutes that are left, it is now, the time is now right for introducing discrete time Fourier series. Conceptually, it's an important concept because it is a precursor to FFT. It is a precursor to the definition of discrete Fourier transform. What we have defined now is continuous Fourier transform. You must distinguish between them. X of n is a discrete time sequence, is a discrete time signal, but capital X of omega is continuous in capital omega. So by Fourier transforming a discrete time signal, you do not get a discrete spectrum. What you get is a continuous spectrum. Alright. Now suppose I had a periodic function. I am talking of discrete Fourier series. As I said, we are playing it low because it is not very much used, except that it clarifies some concepts and it is a precursor to FFT or DFT. Suppose we have a signal x of n plus n. So capital N is its period. Alright. Now you remember that if the signal for a continuous time signal, the Fourier series is AK summation k equals to minus infinity to plus infinity e to the power j omega 0 t. Alright. Now if I want to convert this into a discrete time Fourier series, first let us say because it is discrete time we put a prime here, AK prime. Then instead of t I should write nt, some general, no, not n, I made a mistake. This is k times omega 0. Alright, k times omega. I write it as nt because k goes from minus infinity to plus infinity, and omega 0 is 2 pi divided by the total interval, which is capital N times t. Alright. Now if you simplify this, then don't you see that this becomes AK prime, we will put the limits on the summation a little later, AK prime e to the power j k 2 pi divided by capital N multiplied by n. Alright. This should be the form of a periodic function in the discrete time domain, where k goes from minus infinity to plus infinity. Alright. Now I appeal to your common sense. I want you to look at this very carefully now. Summation a k prime, k equals minus infinity to infinity e to the power j k 2 pi divided by capital N multiplied by n. Now, suppose I write this specifically, alright, k equal to 0 term, it would be a0 prime, k equal to 1 term would be a1 prime e to the j 2 pi by capital N times n, plus etc. Similarly, I have a minus 1 prime e to the power minus j 2 pi by n times n, and so on. And then I have a, suppose I go to the n minus first term, what do I get? N minus 1 prime e to the power j 2 pi by n minus 1 times n. What is the next term? In the next term I get a n prime, and then what is this exponential? It is exactly 1. And therefore there is no point in having so many constant terms. I can absorb a n prime in a0 prime, and similarly I can absorb minus a n prime. So if I call this plus a0 prime plus etc. plus a n prime plus a 2n prime and so on, if I call this an a0, then don't you see that I have absorbed all these constants into one term. You can also see that this term, when k equal to 1, is the same as the n plus 1th term. Alright. In other words, I can combine a1 prime, a n plus 1 prime, a 2n plus 1 prime, and so on and so forth. And therefore, if I absorb all of them in a single term, what I get is that this summation will no longer be an infinite summation. It would be a finite summation. In other words, the discrete Fourier series DFS shall look like x of n equal to summation a k e to the power j 2k, I beg your pardon, 2 pi by n e to the j k multiplied by n, where k is to be taken over just one period. And if I use I can take k equal to 0 to n minus 1, or in general what people write is it is to be taken over one period. Just as integral over one period we say integral 2 pi, similarly summation we simply use this symbol, it means one period. Now you see how simple the discrete Fourier series is. In the continuous time Fourier series you have to bother about doubly infinite number of terms. Here it is a finite number, and the number is precisely capital N. Next time we will show that if you want to find out AK in the continuous time case was found by an integration. Here it is found by a summation, and this summation is over a finite number of terms again. So the discrete Fourier series and its inverse are much simpler than the continuous time case. Alright, we stop here.